Yeah.
Hello and welcome to Math 1000 Geometry Lecture. I am Bo Corkins and let's get to it. So, geometry is a big part of math and especially application math, because it's basically everywhere, right? Shapes and three-dimensional objects, all right? Literally our whole lives exist around this stuff. So, let's start with the basics. A line. All right, a line is right a straight uh, segment that goes in both directions forever. A half line, all right, has a starting point and then goes forever. And notice, all right, the open, all right, circle versus the closed circle. So a half line is excluding that initial point, while a ray is including that initial point. All right, back to our including excluding notation. And then a line segment, all right, has a starting point and a stopping point. A couple of pieces of notation. So parallel lines, right? Lines that run next to each other but never cross. And the big thing here is notice the notation L, two vertical lines, M. All right, with our two lines, that would be L, and that one would be M. So we have our two lines, and so get used to that notation that indicates parallel lines. And then intersecting lines, two lines that cross. When we talk about angles, we're always going to be measuring them in degrees. Now, there's degrees, minutes, second notation, there's radian notation, there's uh, other types of notation, but we are going to be doing only degrees. Now, you can measure these with an old school protractor, but for most things that we're going to do, we are simply just going to label the angles. We have an initial side and a terminal side, all right? And it goes from that initial to that terminal side, all right? And we call the middle value the vertex, and it has some angle, let's call it 30 degrees in between them. All right. If we have a half line, right, and basically a line where the starting point and the stopping point is the same, all right, right, that's just a half line. A couple of types of angles, again, that you're likely familiar with. An acute angle is 0 to 90 degrees. All right, an obtuse angle is 90 to 180 degrees. Right angle, right, which is denoted with this little box. So you'll see that quite often. All right, indicating exactly 90 degrees. And a straight angle indicating exactly 180 degrees. Some notation, all right? So lots of verbiage and notation that we're going to have in geometry. Complementary angles, two angles that sum to 90 degrees. So typically when we write angles, A, B, C, right? So we say notationally, I say angle A, B, C equals 90 degrees. Then I'm going to split this, and I have D. So now I have angle ABD. Notice, right? You start on one side, whatever you're going to call the initial side, you go to the vertex and then go to the other, all right, end of that equation. So angle ABD plus angle DBC, they also equal 90 degrees. They're what we call complementary angles. I can do that similarly with supplementary angles, angles that sum 180 degrees. D, E, F. So angle DEF is 180 degrees. Let's split it. Now I have angle DEG plus angle GEF also equals 180 degrees. And those are what we call supplementary angles. Vertical angles are really, really nice, actually. They just have equal measure. So if you have two angles that cross anywhere, the angles across from each other are equal. So angle AEB is equal to angle DEC. Similarly, angle AED is equal to angle BEC. We write this in notation with a single slash. All right. If you recall your geometry from 9th or 10th grade, we have the angle, and this is the congruent symbol. Similarly, on the other side, I would say, oh, and so notice that you put the two slashes indicating those two are equal, and the one slash those are equal, and then three slashes, four slashes, etc. So that's some notation that you may have seen. So we can solve all kinds of problems with this. The supplement of angle x is 3 times more than the complement of angle x. Find the measures of the three angles. Notice in one sentence, we actually mentioned 3 angles, so it doesn't seem that way. Do this slowly. The supplement, all right, of angle x. So that means angle x, and let's call the supplement of it y. Right? Supplement, by definition, means it sums to 180 degrees. Right? I could also write this, right, as y equals 180 minus x. That's really what that equation is saying. The supplement of angle x, it means y equals 180 minus x. Similarly, the complement of angle x. Let's call that one z. Complement is 90 degrees. Now let's read this again. So if the supplement we're calling y, the complement we're calling z, so z is 3 times more than, sorry, y is 3 times more than z. And now, all right, with one sentence, I basically created, all right, 3 equations. So now with this information, I can take these two guys, plug them into this equation, and I should be able to solve this down for x, and then hence find x, y, and z. Notice once again, rainbow, not going away. Get the numbers to one side and the variables to the other. That gives us x equals 45 degrees. Z is 90 minus that, so 90 minus 45 is 45. And then 180 minus 45 is 135 degrees, which means we have found all 3, all right, of the angles we were looking for. A transversal is really nice. So a transversal, all right, is when you have 2 parallel lines and then a third line that crosses them both. The reason why this is so interesting is it has so many interesting properties of what angles are equivalent, because so many different angles then are going to be equal. So corresponding angles are angles, all right, on one transversal in the same spot on the other transversal. So 2 and 6, all right? 1, 1 and 5, 3 and 7, and angle 4 and angle 8. Those are all corresponding angles. They will have the same measure. Alternate interior angles are pretty fun too. So you have an angle on the inside, still being on the inside, but switching to the other side. That's an alternate interior angle. So angle 4 is equal to angle 5. Similarly, angle 6 is equal to angle 3. And that's actually all the alternate interior angles. Similarly, alternate exterior angles. So angle 8 is equivalent to angle 1. And similarly, angle 2 is equal to angle 7. And then lastly, angles on the same side of a transversal are supplementary angles. They sum, all right, to 180 degrees. So, for example, angle 1 plus angle 2 equals 180 degrees. Angle 1 plus angle 3 equals 180 degrees. Angle 2 plus angle 4 equals 180 degrees. And angle 3 plus angle 4 equals 180 degrees. The concept is, even though we have 7 angles here, you notice a lot of these are the same. There's only 2 different angles, all right? Everything else is an equivalency. So that means if I knew angle 1, I can find the other 7 angles, and that's really, really nice. To that end, let's do an example. So I want to use the properties to find the measures of angles A, B, and C given, all right, these 2 lines are parallel and we have a transversal between them. So super important to notice, I started with 1 angle here. I have about 20 other angles. Okay, actually technically I have 2 angles because I know this guy right here is told to us, all right, with the box here, that means that guy's 90. So I know 2 pieces of info and I'll be able to find like the other like 18, 19, whatever angles that remain. So we can just fill this in 1 piece at a time. If I have 42 degrees right here, that means that's 42 degrees. The angle next to it, angle B, all right, is going to be supplementary angles because B plus 42 degrees equals 180 degrees. So that's 138 degrees. Similarly, vertical angles. This guy is 138. Corresponding angles. This one is 138. This one is 138. Because that's 42 degrees, alternate exterior or corresponding. All right. This is 42 degrees, and this guy right here is 42 degrees. So now I found angle A. Now, that's all the info I can find uh, without calculating something new. So now I'm going to go to this triangle with angle 1, 2, and the right. So first of all, if that guy's a right angle, that also tells me that's a right angle. Well, because of then supplemental, these are right angles. So actually, oh look, because I had one right angle there, I knew, all right, the remaining, all right, three angles. Then, if you recall, triangle property. The angles of a sum of the measure of all the angles in a triangle is 180 degrees, which means angle 1 plus angle 2 plus that 90-degree angle equals 180. Since we're told angle 1 is 42 degrees, then I should be able to find angle 2, subtract 90, subtract 42. Angle 2 is equal to 48 degrees. Now, the biggest mistake I see, notice that I had to have that in-between right angle to find the other transversal. The biggest mistake I see is that people are like, oh, well, that's 42, that's 138. Everything is the same on the other one. It is absolutely not true. You need to use something like a right angle to get to the other transversal and find, all right, what that value is. Once I have that, then with vertical angles, I can find angle C, which is also 48 degrees. Now, typically that's all the question was asking for, but while we're here, let's find the remaining information. So with supplemental angles, that means this guy right here is 132 degrees. Vertical angles, that's 132. Then we can jump all the way down to this other transversal with alternate exterior, corresponding, and vertical angles. And so notice, right? Let's see. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 18. Yes. So we, with two pieces of information, all right, there were 20 angles here. We filled in 18 of them. And that's really, really interesting. So that's really, really fun. Angle measurements, you can do all kinds of fun stuff. Let's look, all right, more in depth at what we just looked at there, the triangle. All right, so triangle, three-sided figure, all right, specifically three-sided polygon. There are three types. Scalene, where no sides are equivalent. All right, all sides are different. Isosceles has two sides, all right, that are equivalent. And similarly, the angles corresponding to those are the same as well. And lastly, equilateral, where all sides are the same and all angles are the same. Without a doubt, the biggest theorem, all right, in all of geometry is the Pythagorean theorem. A squared plus B squared equals C squared. If you have a right triangle, the sum of the square of the legs equals the square of the hypotenuse, the value across from the right angle. Pythagorean theorem is very, very commonly used. For example, a radio tower is supported by a wire that is 130 yards long and attached to the ground 60 yards from the base of the tower. How tall is the radio tower? The reason it's so commonly used is that most of the time in the real world, what we do is right angles. Notice this didn't say, I have a right angle with the ground. It is implied, all right, that the tower and the ground form a right angle. So let's call the height of the tower H. That forms a right angle. I have a 130-yard long wire. That is 60 yards from the base. And oh, look, I have Pythagorean theorem. The equation is pretty simple. Biggest thing, just make sure that you're following your calculation, and I'll actually write it all out here just so we can see exactly what's happening. Subtract 3,600 from both sides. And then square root. When you take the biggest part is just remember to take the square root. I see people forget that quite often. And don't forget your units. And of course, don't forget the logic of it, right? When I see people forget to take the square root, right? If you have, 130-yard long cable, there's no way it's 13,000 yards tall, right? So the calculation, not complicated. Just make sure follow through on the details. This word similar figures is going to come up quite often, and it doesn't always say the figures are similar. But when you have two shapes, right? If I have two circles, or I have two, in this case, parallelograms, or two rectangles, or two squares, the figures are similar because they're ratios of each other. And that's the biggest thing. Notice, right? Side AB, I can ratio to side EF. I can set that up to FG and BC. So you can ratio the sides, and that's just really, really nice. What's even nicer is the angles are exactly equivalent, right? Angle EHG here is exactly EDC. Same thing for all the other angles, all right? The angle in the same spot is exactly the same, all right, for similar figures. To that end, a man who is 6 feet tall has a 4 foot shadow. A lamppost 10 feet from the man has a 14-foot shadow. How tall is the lamppost? Notice it didn't say similar figures, but it's setting up two shapes that are the same shape, and you should then identify they are similar figures. So let's start with the man. He's 6 feet tall, and he's got a 4 foot shadow. Then I have a lamppost, all right, that has a 14-foot shadow. Now, right, knowing what we do, guess what shape we're going to make here? Triangles. And because it's a man and a lamppost, ideally, again, not specified, but these are both right angles. Hence, now I have similar figures. I'm trying to see how tall is the lamppost. And I can set up these ratios. 6 over h equals 4 over 14. Now, be aware, you can set it up as h over 6 and 14 over 4, as long as you keep that consistent. It is definitely not 6 over h and 14 over 4, so don't crisscross them. In order to solve this, what we are going to do, all right, is cross multiply though. So 6 times 14, 84 equals 4h. Divide both sides by 4. H equals 21 feet. So, very, very nice. A big definition we're going to see is polygons. So, before we get into the details of polygons, let's discuss what a closed plane figure is and a simple plane figure. So, a closed plane figure is when you start and stop your pencil at the same spot. A simple plane figure is when you don't pass through it. So, notice in this first example, all right, the figure is connected and it doesn't cross through itself. So that is closed and simple. Notice the next one, simple and not closed. Doesn't cross through itself, but doesn't connect. Doesn't start and stop at the same value. Closed and not simple. All right, so starts and stops, but hourglass, right, crosses through itself. And then not simple, not closed, crosses through itself and doesn't connect. A polygon is a simple, plain, closed figure. Okay, so it doesn't cross through itself and starts and stops at the same point. The big one that we're going to see, though, is a regular polygon. All right. A regular polygon, all sides and angles have the same measure. Now, notice right here, this, all right, regular, all right, hexagon. This actually is not a regular rectangle. A regular rectangle is actually a square, right? All sides and angles are the same. This is a polygon, all right? It's just not regular. There are our other main shape, triangles are without a doubt the most common. Circles are really common. And then the next, probably most common, is quadrilateral, four-sided figures. Trapezoid, all right, where you have at least one side of parallel sides. A parallelogram, both sides are parallel. Rectangle, all right, right? You have two parallel sides and all right angles. Rhombus, all sides are equal, so a specific type of a parallelogram. And then a square, all sides are equal, right? A regular polygon. A nice equation to help us identify the angles of each of measure for a polygon is the n minus 2 times 180. So we already talked about a triangle having 180 degrees. Well, similarly, we have four-sided figures, five-sided figures, which we can use this equation for, right? 4 minus 2 becomes 2, which makes 360 degrees. 5 minus 2 becomes 3 times 180, 540 degrees. And that's the total sum of all the measures within, all right, a polygon. That's really, really helpful because that allows us, when we know we have regular polygons, we can identify the measure of each angle. Let's look at an example here. So I have a hexagon, and it is identified as a regular hexagon. That is one of the biggest things. I have a furniture maker, right, with a chair, horizontal beam, cross section, shape is regular hexagon. Beam will rest in the support post as shown in the diagram. All right. What should be the measure of the indicated angles so that the beam fits exactly into the notch? That means we're trying to find this guy right here. What is this angle? So let's start with our regular hexagon. A hexagon has 6 sides. That means the total measure of all the angles is 720 degrees. Each angle then would be the total measure divided by the number of sides. So each angle measures 120 degrees. Now, by definition. So if each angle is 120 degrees, that means, all right, the the beam here, the cross beam and the support post, right? The two of those angles there form a straight line and hence are supplementary angles. That means what we are calling angle question mark plus 120 degrees equals 180 degrees. So hence angle question mark is 60 degrees. And that's the really nice thing you can do because you know it's regular. Now, the good news is most of our figures are regular figures. It's the vast majority of our figures, all right? Not all, but most. So, all right. One other little simple concept, which you're most likely familiar with, perimeter. All right, we've already discussed this a little bit. Perimeter is just the sum of all the sides. So with some things, we actually have equations like rectangles. All right, but most of the time, just sum up all the sides, and that's how you identify the perimeter. For an example, what will the cost to place baseboard around the region shown if the baseboard is 25 cents per foot and no baseboard is needed for the 2-foot doorway? So I have, let's see, 5, 10. Oh, I'm missing a side right here, but if the side on the other side is 5 and that one's 2, that makes that guy 3 feet. The distance all the way across, which looks like this guy is 15 feet. If that's 10 feet, that makes this one 5 feet. So a couple ways to do it. I can clearly see that it's 15 plus 15 plus 5 plus 5 minus 2. Or I can just sum them all up, and let's do it the slow way just so we can go all the way around. So I see 5 feet plus 10 plus 3 plus 5 plus 2 plus 13, right? I'm cutting out that 2-foot doorway. That gives us a 38-foot perimeter. Then, since we are told the cost is 25 cents per foot, and we have 38 feet. Notice once again, our units will cancel, and this ends up giving us $9.50. So, all right, perimeter is definitely something that you should be familiar with, but we are going to continue to use dimensional analysis and conversions. All right, it is without a doubt one of our huge things that we emphasize. Area is another big one that we like to calculate because a lot of things are area, right? I mean, we were already looking at units with area and things to that nature. So rectangle, all right, we have the equation is length times the width, right? That's how we calculate it. Sometimes we have a perimeter formula. Notice we have the perimeter 2L plus 2W, all right, for the perimeter. A parallelogram, it is the height times the base. Now, important to note, the base is this distance, all right, distance across, and then the height. It's not actually length of the sides, it's base times the height. Trapezoid, all right, 1/2 base 1 plus base 2 times the height. With a trapezoid, you want to be aware that you can also just break this down into rectangles and triangles too. But there's a nice little formula for the area. And our big one, triangle. The one you're probably most familiar with without a doubt, area equals 1/2 base times the height. The one you're less familiar with, this right here, this is what's known as Heron's formula. All right. Heron's formula is if you only know the sides, you don't actually have like the height of the triangle. And that actually is very common. So this is a very useful formula. To that end, let's look at an equation here. I want to find the area of the triangle, right? And then find the height. So notice I have the distance 10 centimeters, 4 centimeters, and 8 centimeters. It is a scalene triangle. Okay, I see we're told we have a right angle here, but if I don't know the height, that means, all right, I cannot use this first equation. I can't use that because I don't actually know, right, what the height is. I have to use Heron's formula. So Heron's formula works like this. Calculate S. S is purely just a means to an end. I use S to calculate A. All right. It is S minus each side multiplied by itself and them all together, then square root the whole thing. So, all right, multiply those out, then take the square root of all the values. That will then get us 15.2. Units are important, centimeters squared. Once I have that, then now I have the area, I can actually calculate the height. So I'm going to use my other equation and I can work that backwards. A equals 1/2 base times the height. The area is 15.2. The base, all right, is 10 centimeters. And the height is unknown. So now I can actually calculate this down to find what the height of this triangle actually is. 3.04 centimeters. All right. Let's look at one more here. So, a base plate in the shape of a parallelogram is shown. All right, we got lots of dimensions. I want to find the plate area and then find the weight of the plate with a conversion. So we just talked about this. Okay, so we got a right angle here. Our picture got kind of off. The area of a parallelogram, okay, is the base times the height. Notice I don't have that. I have a height distance, which I can see, or sorry, a length, a length distance, but I don't have the height. But just like I was talking about with trapezoids, if you don't have all the information, break it down to the two figures that we're the most familiar with, triangles and rectangles. I see two rectangles here and I see a rectangle and two triangles. Since I see that's a right angle, I can actually make a smaller triangle with our distances there. So I see that 0.8082, all right, and 5832, if I subtract those two, I'll actually get the distance, all right, of the base of the triangle. Then I have the height, right? And I see that I have 4676, all right, for my hypotenuse. I am told that is a right angle. And so then, all right, I can solve that using our best and favorite theorem, Pythagorean theorem. I can solve that down to actually find, all right, the height of our triangle, and then we'll be in business. That gives us 0.4099 meters. Now with that, all right, I can calculate the area of the parallelogram, which is base times height. So 0.5832 times the height, which we just found, 4099. Which gives us 0.239 meters squared. And then, all right, the second part of the question said, find the weight of the plate if 1 square meter weighs 68.4 kilograms. So the second part is saying, okay, if we're looking for weight, I have an area. And then I have a conversion. 68.4 kilograms equals 1 meter squared. Notice once again, we can use it to cancel our units, and then it is simply multiplying our values together to get, all right, our conversion. All right. We'll call it a day for there, and we will pick it up in the next geometry video. Have a good day.